Welcome back to The Explainer. Today we're unpacking one of the most astonishing, completely mind-bending phenomena in the entire universe. We're talking about the sheer, bizarre reality of dead stars literally freezing into giant metallic, cosmic crystals. Long after a star exhausts its fuel and dies, it doesn't just fade quietly into the dark. Because of a quirk in quantum mechanics, its core undergoes this massive phase transition. So in this explainer, we're going to break down the exact mechanics of how this happens, mapping out how the universe is quietly filling up with crystalline spheres the size of entire planets.
So, here's the central question we got to answer. In our everyday experience, freezing is something that happens when things get, cold, right? Water turns to ice at 0 degrees Celsius. But in the ultra-dense core of a dead star, those rules change entirely. We have to wrap our heads around how a roiling, boiling ocean of carbon and oxygen plasma can actually freeze and turn into a solid structure, while the temperature is still hovering around a blistering 10 million degrees Celsius. It's totally counterintuitive for sure, but the physics behind it are absolutely fascinating.
Okay, let's dive into this. To understand this weird kind of freezing, we first have to understand the environment. 1.4 represents the maximum solar mass, so about 1.4 times the mass of our entire sun, that can be packed into a stellar remnant roughly the size of the Earth. Just imagine taking our massive sun and crushing it down until it's the size of our home planet. The matter inside is so incredibly compressed that a single teaspoon of it, if you brought it here to Earth, would weigh about as much as an elephant. Literally several tons in a single teaspoon. It's an environment of unimaginable extreme pressure.
To solve this cosmic mystery, we're going to take it step by step. We'll hit the birth of a white dwarf, the physics of dead stars, turning plasma into crystal, latent heat and sinking elements, evidence from the stars, and finally, resetting our cosmic clocks.
Section 1. Birth of a white dwarf. Let's establish what exactly we're dealing with here. The vast majority of stars in our Milky Way galaxy, I'm talking over 95% of them, and that includes our own sun, will end their lives this way. When a star exhausts its hydrogen and helium fuel, the fusion engine just stops, and without that outward pressure, the star becomes unstable. It expands into a red giant, its self-gravity weakens, and it violently sheds its outer layers into space, creating this temporary, incredibly beautiful planetary nebula. But what is left behind is the core. Just this inert, super-dense, glowing object that isn't producing any new energy of its own via nuclear fusion. It's just glowing with trapped residual heat.
Section 2. The physics of dead stars, which immediately brings up a huge physics mystery. If there is no nuclear fusion pushing outward, why doesn't this incredibly massive, dense core just immediately collapse into a black hole under its own crushing gravity? Well, the crucial point is the difference between what holds up a living star and what holds up a dead one. Living stars are in a constant tug of war. Gravity pulls in, but the thermal pressure powered by nuclear fusion pushes out. A white dwarf, though, has no fusion. Its survival relies entirely on a quantum mechanical effect called degeneracy pressure. The matter inside is squeezed so hard that the atoms are stripped of their electrons, creating a compact sea of bare nuclei floating in a really dense gas of free electrons. This is the Pauli exclusion principle doing the heavy lifting. It basically dictates that no two electrons can occupy the exact same quantum state. Think of it like a highly crowded room with a fixed number of chairs. Once every single chair is taken, nobody else can sit down, no matter how hard you push them into the room. Because these electrons cannot be squeezed into the same state, they push back against the crushing weight of gravity. And what's truly amazing is that this outward pressure is totally independent of temperature. Even if the star cooled down to absolute zero, that electron degeneracy pressure would still hold it up.
Section 3. Turning plasma into crystal. So we have this dead, degenerate ball of carbon and oxygen plasma, glowing with leftover heat, just radiating it out into space. Initially, a white dwarf is blisteringly hot. Surface temperatures can easily exceed 100,000 degrees, and the core? Vastly hotter. But it's constantly losing heat. When the core eventually cools down to roughly 10 million degrees Celsius, something dramatic happens. Remember, the pressure here is millions of times greater than anything on Earth. At these extreme densities, the physical state of the matter heavily depends on the composition of the star, and the ratio between the electrostatic energy of the ions and their thermal energy. Let's break down exactly how this builds. Step 1, as the white dwarf cools, the thermal motion of the atoms starts to slow down.
Step 2. As that heat drops, the Coulomb interactions, which are the electrostatic forces between those positively charged atomic nuclei, start to overpower the thermal motion that's trying to keep them apart. And then step 3. A first-order phase transition happens. The carbon and oxygen ions literally freeze. They lock into a highly ordered, rigid, body-centered cubic metallic crystal lattice. The entire star is essentially turning into a solid crystal from the inside out.
Section 4. Latent heat and sinking elements. Now you might be thinking, okay, it freezes, it keeps cooling, end of story, right? Actually, no. Observers started noticing a massive anomaly.
These white dwarfs seem to be stalling out. They were staying hotter for way longer than standard cooling models predicted. So why the stall? It comes down to 3 massive energy sources. First, when the plasma turns to crystal, it releases latent heat, exactly like water releasing energy when it turns to ice. Second, because the heavy oxygen crystallizes first, it essentially snows out and sinks to the core. Oxygen is heavier than carbon, so this oxygen-rich solid sinking means the lighter carbon-rich liquid rises. This creates a massive gravitational heat engine, releasing huge amounts of potential energy. And third, if there are trace impurities like neon-22 in there, they can undergo a distillation process, separating and sinking or floating. Scientists now believe this specific process causes extreme multi-billion-year cooling delays in the most massive white dwarfs.
Section 5. Evidence from the stars. That is a beautiful physical theory, but how do we actually prove this is happening out there in the void?
We can't exactly send a probe to drill into a white dwarf. The answer lies in looking at large populations of stars. Over 50 years ago, a theorist named Hugh Van Horn predicted that this crystallization would release latent heat and slow the cooling down. Astronomers finally found the empirical evidence by looking at globular clusters like NGC 6397. By graphing the luminosity of thousands of white dwarfs in that cluster, they found a distinct peak, a literal pileup of stars just hanging out at a specific brightness. They were stalling because their cores were freezing.
And this brilliantly illustrates the massive breakthrough provided by the Gaia space mission. Gaia gave us incredibly precise distances and luminosities for tens of thousands of white dwarfs. When researchers plotted all that on a Hertzsprung-Russell diagram, they found a massive, undeniable transverse sequence. It's a pileup of white dwarfs right at the exact temperature and luminosity where our models predict crystallization happens. The stars hit this phase, their cooling slows down dramatically thanks to the latent heat and that sinking oxygen, and they just sit there on the graph for up to 1 billion years.
That Gaia data also revealed what's called the Q branch, where massive white dwarfs experience an absolutely inexplicable 8 billion-year cooling delay, which is likely driven by that neon-22 distillation we touched on. But here's the thing, population data is tricky. To really test these models, we need individual white dwarfs with known ages. Enter a star system called HD 194-112. This is a Sirius-like quadruple star system just 32 parsecs away. It contains a crystallizing white dwarf bound to 3 normal main sequence stars. Because we can easily calculate the age of those normal stars, we know the total age of the system. This gives us a highly precious external clock to directly measure exactly how much crystallization is delaying the white dwarf's cooling.
Section 6. Resetting our cosmic clocks. And this brings us to the most profound implication of this entire phenomenon.
Because you see, this isn't just about dead stars. It's about how we understand the timeline of the universe itself. For a very long time, astronomers have treated white dwarfs as our cosmic clocks. Since they have no fusion, their evolution should largely be a simple, predictable cooling process. Measure how cold a white dwarf is, wind the clock back, and you theoretically find out exactly when it formed. That helps us date stellar populations and the galactic disk itself. But crystallization? It throws a massive wrench into those calculations. If these dead stars are generating their own internal heat engines through freezing and chemical separation, they are actively hiding their true age, appearing much, much younger than they actually are.
I want you to take a second to process this quote from the researchers. Billions of white dwarfs in our galaxy have already completed the process and are essentially metallic crystal spheres in the sky. The sheer scale of that is staggering. This isn't some rare anomaly. It is the ultimate fate of over 95% of all stars. It means that our own sun, billions of years from now, will shed its outer layers, shrink down to an Earth-sized core, and eventually freeze into a translucent metallic crystal tombstone lingering out there in the dark for a quadrillion years.
So, what does this all mean? We rely on the stars to tell us the story of the universe, but if this invisible quantum freezing process has been quietly injecting heat into dead stars, stalling their cooling by billions of years, our cosmic clocks have been ticking significantly slower than we ever realized.
If that's the case, we have to ask ourselves just how old is the galaxy around us really? It's like a giant puzzle. Think about that, and we'll see you in the next explainer.